Hello, welcome back. So today we 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 have a very short lecture, which I give more for completeness than for providing via in-depth information. Uh, the question that I'd like to very superficially scratch in this lecture concerns what is the quantum analogy of the Langevin equation. So in other words, we discussed quite in depth in the several last lectures whether it is possible to describe an equation of motion that simultaneously takes into account of the effect of a path without having to explicitly simulate or follow the dynamics of the path. And the Langevin dynamics does precisely this, right? It modifies Newton's equations with additional terms and allows you to include in one shot the effects related to the fact that the system is not closed but is in contact with a heat bath, in fact. So we have gone from this equation to this equation, where these two additional terms were those which accounted for dissipation and fluctuations respectively. And then we went from this equation to this equation, which is basically the Markovian limit of the previous equation in configuration space. Uh, Once again, in the case of classical dynamics, when we define Markovianity, since the equations of motions can be turned into first order in phase space, it turns out that the Langevin equation is Markovian in the phase space, while the overdamped Langevin equation is Markovian in configuration space. But basically, when we go from this equation to this equation, we make an assumption about Markovianity, but already in configuration space. But already when defining this term and this term to obey delta correlated fluctuation dissipation relationship, we are making an assumption about instantaneous loss of memory of correlation in the bath. And that together is the main assumption of Markovianity in some sense. Whether then you want to make it super Markovian and be Markovian directly in configuration space or in phase space. It's a matter of detail. Now, what we would like to do today is to sort of build the same chart at the quantum level. So basically start from a Schrödinger equation and derive an equation that is the most general equation that accounts for the effect of the path. This equation will be extremely general, and like most extremely general equations, will be sort of relatively useless. However, if you in additionally take a Markovian limit and assume that the path is very fast decorrelating, you get another type of modified Schrödinger equation, which this time is more useful because it's practically implementable. To me, a very general criterion that I always adopt to say when some theoretical framework is useful or when it is not is whether I can easily teach a computer to do this. And if a computer can do it, well, then it's useful. If the formulas are too complicated for a computer to be able to sort of turn it into numbers and crunch numbers, then it's sort of useless for practical application. It might be useful for conceptual things. So In this lecture, I will not try to derive anything. I'm basically telling you what is the analog at a quantum level and for you to be aware of it, essentially. It's not something I have the, so to say, the ambition in this course to go in depth with. And to be honest, it's not something I'm an expert of. So two things often go together. One goes deep on things he's sort of an expert of and chooses not to go too deep when things are not in his own expertise. Okay, so we will work directly at the level of density metrics because remember, when you are in an open system, the wave function is not appropriate mathematical concept because an open system are subject to a phenomenon that is called decorrelation or dephasing, and dephasing essentially implies that you can never write a wave function as a bracket in terms of a single wave function, but you have many wave functions with different probability, no matter what base you choose. So let's begin by rephrasing Schrödinger dynamics, this time in the language of the density matrix. So that's my system plus Bath equation of motion for the quantum density matrix. And you know, this is a Steiner-Liouville von Neumann equation, right? Liouville von Neumann equation. Now, I want to emphasize that this is an operator. So this is an operator-valued differential equation. In addition, what is on the right is an operator acting on an operator. In other words, you have a Hamiltonian which commutes with the density matrix. So this object here, which takes an operator in input and returns the commutation relationship of that operator with a given operator, is, if you want, an operator that acts on the space of operators. So this is called a superoperator. So in the von Neumann equation contains a time derivative of an operator, which of course is implicitly assumed to be in the Heisenberg representation. And on the right-hand side, it contains a superoperator that determines how to evaluate, given a physical theory, given the physical theory are defined by the Hamiltonian, how to evolve in time your density matrix. Now, what we want to do is to construct a differential equation for a reduced density matrix, which corresponds to this density matrix where I have performed the trace only over the Bath variables. So basically, I'm a density matrix that I will call rho reduce, which corresponds to the trace only on the Bath variables of my density matrix. Now, B is some base in the Bath, defining the Bath. Now, it can be shown that once you trace out over my Bath variables, let me define my Hamiltonian to be like H tot is equal to H plus H Bath system, which describe the Bath and the system. Oops. So after I do this, it turns out that my Schrödinger equation is modified once again into a new Schrödinger equation, which now contains the superoperator, now restricted to the system. And that is the analog of the Newton's part of the Langevin equation, if you want, plus, in general, another superoperator, which acts with an eye on the. under the reduced density matrix. This is a non-unitary superoperator. I'm going to move my face in a moment. And together, this equation is called quantum master equation. Once again, the way it works in practical application is on the other side. You say, okay, that's the general form of my Schrödinger equation or you will find Neumann equation when I have an open system. In addition to my internal Hamiltonian, I have to add a non-unitary superoperator. Fine. What non-unitary superoperator? Of course, there are infinitely many possible non-unitary superoperator. And in principle, depending on your microscopic system, you might perform the trace, and given a specific trace, under certain assumption, you come up with particular forms of this superoperator. For instance, if you take a trace of a harmonic oscillator, and on top of that, you make some memoryless assumptions of decoupling assumption of frequencies, as we did in the Langevin equation, we might be able to construct a specific form of this non-unitary superoperator. But at the moment, if I do not specify anything about this equation is as useless as it gets, because I don't know what it is, and therefore I could do nothing with it. But the general structure is called the quantum master equation. Now, in addition, now we get a little bit more practical. If we assume Markovianity, then the quantum master equation can be cast in the following form. Well, this part we now know is the same as in the previous slide. But this is the different part. Again, I'm going to move my face from the screen in a moment. Put it here, take it back. So what this equation is telling me, so where L and mu goes from 1 to n, generically defines a set of operator in Hilbert space, non-self-adjoint, because L and L dagger are different. So the assumption of Markovianity, stated differently, basically enables me to restrict the possible form of the D superoperator that I was referring to before to be in the form of a sum over a set of operators. Mu is the label of n operators, L, mu, and a sum of commutators of L including L mu and L dagger mu in the form that you write here. Stated differently, what I'm just saying is that in the Markovian limit, the superoperator D is 1 over h, and I guess there's an I missing somewhere in the notes. I have to fix it. but never mind, up to an I. At this level, I'm realizing as I speak. Where the dot is where the argument of this superoperator goes. So this new equation is often referred to the Lindblad equation, or more properly, the Gorini-Kostanovsky-Sudarshan-Lindblad equation. I usually read it as a Lindblad equation. And it's the equivalent of the memoryless assumption in the Langevin dynamics. Once again, this is not yet an operation, an equation you can teach a computer to solve unless you specified your set of new operators. But is a more specific form of operators, which reflects the Markovian behavior of the system. I'm aware that this lecture is not teaching you anything, except it's more like a zoology question of a lecture, right? In zoology, you just learn about things that exist, and you become aware of distinctions between fungi and licheni and whatever, mammals and reptiles, and you take awareness of something. In physics, and in both the theoretical and experimental physics, but in this case, in theoretical physics, we are more used to learning by deriving, by understanding how you get to something. And just for you to be aware, I'm not expecting you to be able to derive these objects. I'm just making you aware of the fact that they exist. Now, I will try to hunt for a missing I sign somewhere. If there is any missing sign, I think there is, and in that case, I'll correct the notes on the web. But if you Google otherwise, quantum master equation and Lindblad equation, you'll find the results for the correct I sign. Okay, this closes my very, very short discussion of quantum dynamics in open system. You'll find this material in the notes. You'll find more material in the notes, because I'm also in the notes I take the care of defining also the Matsubara formalism and the real-time quantum dynamics formalisms in language of Green's functions and stuff. Whatever I don't teach in class is not part of this course. In my notes there is more material than I ask you to know. Okay, I could give one more lecture on statistical mechanics of classical open system concerning applications and enhanced sampling methods. And after that, we'll move forward to the second part of the course. And the second part of the course is about field theory, statistical field theory, meaning use of concepts of fields and path integrals to study statistical systems. And I will mostly concentrate, if not entirely, we'll see as we go, on statistical mechanics of classical systems defined by fields. The interesting thing is, as we shall discuss next lecture, that the same identical formalism, basically with the only exception of having to carry around an I, unitary image, imaginary number around in formula, basically extends to study scalar fields or bosonic fields or vector fields in quantum field theory. I will ask you to have no quantum field theory knowledge. But basically, whatever I'm going to be saying will be useful for Klein-Gordon fields and for vector fields in quantum field theory. The discussion of fermionic fields is in path integral formulations is an entirely different matter. can be done, but it has limited, not zero, but limited application in classical statistical mechanics. Has some application in polymorphic theory and other stuff. But okay, I think that's it for this part of the course. I will probably give one more lectures on enhanced sampling, and then we'll move forward to fulfill. Goodbye.